Okay, so here we still have two additional examples to finish off this chapter. So the first one is like this. So a long coaxial cable consists of two thin wall concentric conducting cylinders with radii A and B. The inner cylinder carries a steady current I, and the outer cylinder provides the return path for that current. The current sets up a B field between the two cylinders. Calculate the energy stored in the B field for length L of the cable. Okay, so here it says we have a coaxial cable, long coaxial cable， 就是一个同轴的一个的电线吧，电缆。这电缆的话好像一捆的这样，但是这是 cable。那 coaxial cable 一般是用来传一些比较高频的讯号的 coaxial cable， 就是说它其实有两个同轴的一个圆柱形嘛。那外面那一个实心的黑色跟里面那个实心的黑色，那这个只是那个什么高斯面，还不是高斯面，那个只是一个ampere loop 啊 ，ampere loop。This is the ampere loop. So this one does not physically exist. Okay, so we only have this inner cable and then the outer cable. So they are the coaxial. So actually, when we try to transmit the signal, we transmit in one of it, and then the other one is so-called the return path. 就是要有一条路哦，你传过去，另外一根的话就有一个信号同时回来的，那这样的话才能传一些比较高频的讯号。Okay, so in such a way, it asks us to calculate the energy stored in the B field, okay, between the coaxial cable. So of course we will make use of Ampere's law. Okay, so integration of B dot ds equals mu0 I, because we have I, we have let's say I going into the page or out of the page, and then the other one is going in the opposite direction. And then if we define the ampere loop between the inner loop and the outer coil or the outer cable, okay, so the only enclosed current is the inner one. So just as what we did before, this is nothing but B times 2 pi r, and then we have a mu0 I. Okay, I is the static current. Okay, so we can quickly get B equals mu0 I over 2 pi r, which is a very popular formula in chapter 29. Okay, so in such a way we can calculate UB to be B squared over 2 mu naught. So which is nothing but mu0 I mu0 I square and then 2 pi, let's see, this one should be 8 pi square and then r square. Okay, because here we have mu square partly cancel with this, we have a mu naught here, and then partly cancel with this mu naught square. So we only have a mu square, and then 2 square multiplied by 2. So here we have 8. Okay. Okay. So finally, dUB is actually UB times dV. Okay. So this is the energy. Actually, the energy at that part, which is the energy density multiplied by that small volume. So this is UB is this one mu0 I square over 8 pi square r square, and then multiplied by dV. Okay, so actually this dV is somehow like r, dr, d theta, dz. Okay, this is for the cylindrical coordinate. Cylindrical coordinate is somehow like we have something like this. This is x, y, and z. Okay, so you can separate into a z-axis with a polar coordinate. So this is the area for the polar part, polar coordinate. dA for the polar coordinate for polar coordinate 极坐标的面积是这个 r d r d theta。之前有说过很多次了，就不重复，乘以一个高度。Okay, so this is actually UB. This is actually big UB. Okay, let me write it like this. UB equals integration of dUB. Okay, becomes this thing. Or we have some constant mu 0 I square over 8 pi square are all constant. So we can just put it in the front, and then we have a dr, and then we have r and then r square. So finally we only have over r, and then we integrate from a to b. We just consider this part. Okay. Consider this part. Okay, and then for d theta, it is d theta from 0 to 2 pi, and then dz from 0 to length L. Okay, length L. Okay, so actually maybe we just go to here. Okay, it is actually mu 0 I square over 8 pi square. This one is lateral log of r, and then evaluate from a to b. So this is actually lateral log of b over a. This is lateral of b minus negative lateral log of a. So this is lateral log of b over a. And then this one is nothing but 2 pi, and then this is nothing but small l. Okay, so finally we have the closed form expressions like this. Okay, and then we can do some cancellation. We can cancel this pi with this pi square, and then cancel this 2 with a down to a 4. So finally the expression is like mu 0 I square small l over 4 pi, and then times natural log of b over a. Yeah, it's somehow similar to the cylindrical capacitor. The expression is somehow similar to that one. If you're interested, you can try to compare them. Okay, so actually for the question B, it asks you what is the stored energy per unit length of a cable if given this value, which means we just need to plug in the values in the previous expression, except we find UB over L in terms of something, because it asks you the energy, store energy per unit length. Okay, so we only count UB over small l to be mu 0 I square over 4 pi, and then times natural log of b over a. Okay, so we can just plug in all the values. Okay, mu 0 over 4 pi is 10 to negative 7, and then times I is 2.7 quantity square, which is this one, and then times natural log of b over a, which is 3.5 over 1.2. Okay, so this is nothing but 7.8 times 10 to negative 7 joule per meter. Joule per meter, like this. Okay. Okay, so this is quite interesting. Okay, so and then the final one is somehow like this. Yeah, so it says two parallel loops of wire have a common axis. The smaller loop radius r is above the larger loop. Okay, so we have two loops, one larger one and then the smaller one, and then this one is higher. This one is higher, and then by a distance x, this x is much larger than this capital R. Although in this figure x and r is yeah, similar. It is a little bit longer than r, but yeah, actually it says x is much longer than capital R. And then consequently, the B field due to the counterclockwise current I in the larger loop is nearly uniform through the smaller loop. Okay, so we also, so actually also hope to satisfy this assumption so that it really needs this axis much larger than capital R, so that the B field generated by this larger loop here, we can consider it as nearly uniform. Okay, to satisfy this assumption. And then finally, suppose that x is increasing. X is increasing means this distance is increasing. So it's somehow like this is at rest, and then this smaller loop is moving upward. Okay, so in such a way, x is increasing, and constant rate v equals dx dt. And then find an expression for B field through the area of a smaller loop as a function of x. Okay, so we will like to make use of this. B field generated by the magnetic dipole. Okay, here we already assume that this x is much larger than capital R. In the previous example, yeah, we just use x to be or z equals 0. Okay, so in the denominator we still have something like z squared plus r squared, and then to the 3/2 power. But here we already assume that r is much smaller than x, so we only have this one. And of course here this z should be x in this question. Okay, so here we have actually b equals mu0/2 pi and then mu over x cubed over x cubed. And here we try to find the phi b of this loop generated by the B field of the larger loop. So phi b we approximate to be b times a, which is mu0/2 pi, and then here this mu is the magnetic dipole moment. So if you still remember, this is NIA. Here we only have a single time, so N is equal to 1, and then it remains I times A. A is the cross-section area, so which means that it is the area of the larger loop. So which is I times pi capital R squared. Okay, so here we have a I times pi capital R squared, and then over x cubed. Okay, and then times this A refer to the area here. Okay, so this is actually for the R area of a small one. This is referring to the larger one. Okay, so we need to distinguish. Oh, this is the source. This is the source. Yeah, so we need to see this one. This one is actually come from the larger loop, and then here, this phi b, we are actually finding the magnetic flux for the smaller loop. Okay, so this area should refer to this smaller loop. Okay, so this one is actually pi times small r squared. And then we can do some cancellation. This pi and this pi, and nothing else. Okay, so finally it turns out to be pi mu 0, and then we have I small r square and then capital R square over 2x cubed. Okay, so this is actually the expression of the magnetic flux, as a function of x, Okay, it's something like this. Okay, so for question B, it asks, in the smaller loop, find an expression for the induced EMF and the direction of the induced current. Okay, so here we will need to make use of the Faraday's law. Okay, so E should be negative d phi b dt according to Faraday's law, and we only have a single term, so the capital N is 1. And here we can just plug in the expression here into here. So, and actually we can notice that this x is related to t. It's a function of time, and all the other things are not time varying. So we consider all these things are constant. So we just put all of them to the front. So we have a negative pi mu 0 I small r square capital R square over 2, like this, and then we have a d dt, and then we have a 1 over x cubed. Okay, all this thing in here are actually constant to time. Okay, not time varying. So we just put it in the front, and then this x is a function of time. This is a function of time. So we need to remain it inside this derivative. Okay, so finding this derivative is you need to be a bit careful. So it is actually, so you can consider it is d dt. This thing is actually d dt and then x to the negative third power. So this one should be negative 3x to the negative fourth power, okay, according to the power rule. But these x and t are different, so we need the chain rule. So we have a dx dt. Okay, so this term is due to the chain rule. This is the product rule. Okay, so here we just put this expression into here. So we have a negative pi mu 0 I r square capital R square over 2, and then times negative 3 over x to the fourth power, and then times dx dt. And actually this dx dt is actually v according to the question. So finally we have two negative signs, so they cancel out. We have 3 pi mu 0 I r square capital R square v over 2x to the fourth power. So this is a quite complicated expression. And finally, it asks you what is the direction of the induced current. Okay, we can make use of the Lenz's law. So here, this is the direction of the current. This is counterclockwise, which means that we can use right-hand rule. So that we know that actually the B field is pointing upward. B field is pointing upward at this point, generated by this larger coil. And as much as this one is going upward, so the magnetic flux going through this smaller coil is decreasing. Okay, it's decreasing. So if it is decreasing, which means that the B external should be pointing upward, so that to counteract this B field decreasing. Okay, so in such a way, the current should be counterclockwise. Okay, the I induced. So I induced, this is I induced. So I induced, for question C, I induced is counterclockwise. 是逆时钟的 ，OK。OK。